talk to you about a little toy project I made to sort of give me some insights into the different ways that you can write C++ to allow me to compare and contrast them, which is interesting because normally I just sit here and talk about CPU cycles and cache misses and show you compilers and things like that. So I just realized there isn't a single compiler explorer link in this presentation, which will shock many of you, I'm sure, myself included. This is, so fair warning, this is another version of a talk that I gave a couple of years ago. So if you've seen this before, you can nod off, that's great. But obviously every time I present it, something new comes out, I'm sure. And I have updated it a little bit, and I've spent the last few days revisiting some of the more curious results I got at the end with not trying to spoil too many things. They kept me up rather too late last night. So there are some late breaking changes towards the end. So stick around is what I'm saying. So there's a story behind this. I like to have a story. And many people come to me and say, how did you learn programming? How could I learn programming? How could I learn this language or a new language? And, you know, what's the best way to do that? And I say, I don't really know, but I thought to myself, how have I approached this myself? And the way that I typically have tried to learn either a new technique or a new language or anything new really is to get on and do. Now, many people learn in different ways. My youngest son, for example, seems to be able to learn just by listening to things, and that seems to do for him. But for me, I have to get my hands on the keyboard and do something or actually get involved. And so the way that I've always learned new technologies or new programming languages is by coming up with a little project that's short enough to be achievable without too much effort, and really importantly, has something interesting and exciting as its output. So some examples include when I was teaching my kids Python, just a Mandelbrot using just ASCII. You know, it's a 24 lines of code, and we hacked around with it, and you run it, and you get a picture. It's not a very good picture, but it's something interactive, and you can go, wow, that's cool, and then you could iterate from there. It can go wrong in certain ways. I decided to prove to myself that JavaScript was far too slow a language to ever write anything significant in, and then ended up writing a BBC Micro emulator that this takes up rather too much of my spare time, both playing the old games I used to play when I was a teenager and fixing the bugs that I find in them. And so I thought to myself, what if I applied this learning technique that I have to C++ itself? I'm kind of stuck in my ways. I have a particular way that I write my code. But what if I said, how about I treated C++ as 3 different programming languages and approached it, writing the same thing in those 3 styles and sort of see what I learn about it, and learn what I learn about myself and the language. So I implemented a path tracer, and we'll talk about what that is in a second. But before we get too far into this, I want to make sure that I'm clear about what this talk isn't. And it's definitely not expert advice on what path tracing is or how to write a path tracer, or indeed an optimal fast path tracer. But and it's also not really, I'm not the source or font of knowledge for what constitutes particular styles, because many people can argue about different things. And so you'll see that the styles that I've chosen and the way that I've chosen to implement them are slightly caricatured to kind of prove a point. So, you know, give me a bit of the benefit of the doubt there. And it's absolutely not me giving you advice that a particular style is the one true style that we should all pin our colors to. That's not what this is about. It is, though, my interpretation of 3 distinct styles. It is real code that does real things and produces nice pictures. And hopefully you'll find it interesting and fun, and we'll learn along the way. And at the end, there's a bit of a twist, as I say, that hopefully you won't see coming. I didn't see it coming, so there's a clue. So what styles am I going to be talking about? Object-oriented is the first style. That's kind of my home style. I tend to write code in a very OO-ish way. So I figured I should have a baseline of trying to be almost exaggeratedly object-oriented. Functional was the, if I can press my clicker, there it is. Functional programming. Now, I'm not an FP person. I don't really understand all the different subtleties of it, but I've spent some time writing in some more FP-ish languages along the way. And I'm aware of some of the M word, you know, monad type things that you can do and all the cool, pure stuff. So this is my interpretation of writing functional style C++. And I'm sure that there are many people in this chat right now that know more about what real FP is, and you can correct me in the comments or in the chat. But this is my take on it. And then the third style, which again, there will be more people in the audience who are far more expert than me at this, is data-oriented, which is a sort of performance-focused style for getting the most performance out of a system by thinking about it from like the performance and the data upwards, as opposed to from like the highfalutin algorithms downwards. And that's very common in the games industry. And I know we have, well, Epic is sponsoring this, so I'm sure that you'll have some things to say about this, especially those who are working on the more performance side of things. So what is path tracing? Sorry, my dog has just decided that he's going to go underneath my chair and he's now poking around. So if I suddenly disappear, it's because he's pulled the Ethernet cable out. I don't get this at work. Yeah. So path tracing, it's very similar to ray tracing, which I'm sure, oh, well, there goes my mouse. Sorry, everyone. Let me get that back before it gets eaten. There we go. It's very much like ray tracing. So if you've heard of ray tracing or you've seen ray traced images, path tracing is like a generalization of ray tracing that can generate extremely photorealistic images. And this image here was generated by some code by someone called Kevin Beeson, who published it on the internet. And the key thing about path tracing is that it's actually relatively simple. I mean, so is ray tracing too, but path tracing doesn't have some of the limitations that ray tracing does. You can see here in this image, it maybe doesn't come out as well in the compression artifacts, but there's a light source at the top. There are these two different spheres, one's sort of more metallic and one's actually clear. And the red wall here is kind of bouncing off and giving a sort of pink hue to the light, the white ceiling. And there's a blue hue on this side. So there's a lot of complicated interactions that are difficult to model in any other way that just come naturally out of path tracing. And when I say it's not much code, this is pretty much all the code. There's 100 lines of C++ of a sort. And I mean, it's kind of cheating rather heavily. But look, it's even got comments, right? I mean, that's not too bad. 100 lines of C++ can generate that image you just saw. And absolutely everything is in this. And it's even multi-threaded. There's some pragmas that you can't see. I think I took them out to make it fit. But there's some pragmas to make it like multi-threaded using some clever trickery. And so it's, in theory, it's not that much code, which is good because I'm going to be writing this 3 times to prove a point. And if it's too big and too complicated, then I'm going to get to the second time and give up. Let's give you a kind of an idea about how path tracing works. It's all about tracing the radiance, which is the light that's coming from a bright object around a scene. But we're going to start from the screen and work backwards. Again, very familiar to those who have done ray tracing. So in this scene I've got here, we have an eye point, which is where like the virtual camera is. There is like a point where the screen is imagined to be slightly in front of the eye. And then for every pixel on the screen, we can take a line through the eye point, through the middle of that pixel, and say, how might light have made it to this part of the screen? What ways can light get here? And so we look down a ray that goes through the eye, the screen, and say, where could the light have come from? And so in this instance, we hit the sphere, and the sphere, we look at the sphere and say, okay, we collided with this part of the sphere. How did the light get to this part of the sphere, right? At the moment, we don't know where, we haven't seen anything that's bright. We take a plane on that point that we intersected, and we say, somewhere in this sort of hemisphere, this sort of half sphere around the point where we collided, there must be light coming in order for light to bounce off and hit the pixel that we were looking at. We will make a guess. Let's pick a random direction, this green arrow, sure, that way, and say, hey, I wonder if there's light coming from that ray. And we follow down that path till we hit something else, and then we follow from there, and we follow from there. We keep bouncing around until eventually we either give up because we didn't find anything that actually had light intensity, or we hit a light source. And when we hit a light source, we know that we've got some light, that there is a path from that light all the way back to the eye, and we can multiply and the colors that we hit along the way, or we can give the materials of the objects that we collided with an opportunity to say, how would the light have been modulated if it bounced in this direction? Now, you're probably thinking something here, which is like, what are the chances of you actually hitting a light? And you're right, you know, if you're doing random bounces, you're not going to hit a light. This is where ray tracing and cheats and goes and looks at all of the lights and says, I wonder if it came from that light. But path tracing doesn't. Path tracing just says, I guess we keep trying. We keep trying and we keep trying and we keep trying. And so the overall algorithm is, for every pixel on the screen, fire a zillion, which is not really a number, rays into the scene, find where light may have come by bouncing around randomly at each intersection point, accumulating the intensity of the light and what color it would have been, and then just average it out. And just assume that if you do enough of these random rays, you're going to get a sampling of the light that could have possibly made it through that particular pixel on the screen. So as you can see, it takes quite a lot of bounces and it takes a long time to render an image. But in theory, every possible way that light can make it from light sources through various reflections in the room to the point in your eye is accounted for. Okay, so we're going to go over this a little bit as we see code, and there will be a fair amount of code, I'm afraid to say. My path tracer is very, very simple compared to commercial quality things necessarily, right? I'm writing it 3 times. It only supports simple materials, and a material is a name that's used in graphics to mean the sort of the surface properties of an object, how shiny it is, what color it is, whether it's textured, whether or not it has transparency, what index of refraction it would have if the light were actually to go through it, all those kind of properties. That's what we call a material. I realize materials are a very overloaded word in English. My path tracer has very simple materials. It also only supports spheres and triangles. I don't have anything more complicated than that. It just is relatively straightforward. And I don't have a scene file format. I can't export anything from like a commercial package very easily anyway. I'm just defining the scenes in code. So I have several scenes that I've made up in code that I'm going to be rendering, and that saves a bunch of IO. And the reason for this, again, is because I have to write this 3 times, and there's only so much code I want to duplicate 3 times. And to give you an idea of the kind of images that my little piece of code can produce, these are 2 images. There is this is a very famous Cornell box, which at Cornell University, they took a photograph, a high quality photograph of the inside of a box with certain properties. And that's been used as a benchmark ever since to say, like, well, can we render the same scene and have it indistinguishable with the measured properties? And this is totally distinguishable from a real one. I get it, but it's not far off of it. And then this is the monkey that is the logo for the open source package Blender. And both of these I got from a friend of mine, Michael Fogelman, who also dabbles in this kind of stuff, and he's got a Rust-based path tracer. And again, I just sort of imported them into the code and rendered them. And they look pretty, and you get pretty images, right? You get it right, you get a pretty image. Admittedly, if you get it wrong, you get a black image, or you just get like some complete garbage. But you still get a reward, a little bit of an endorphin rush when you run it and you get something nice. So I said that I have to implement this 3 times. And there is a little bit of boilerplate that I decided I would not try and make object-oriented or functional or DODE. And that is like a basic maths library. So I'm going to be doing a bunch of intersections between lines and spheres. I'm going to have normalized and unnormalized vectors. And I'm going to have some other bits and pieces that just don't make sense. I do them either once or twice for the whole image, like setting up a camera and all of the maths that needs to go in order to work out where the lines go through each pixel. And all of that, I'm just going to write once and then pop in a utility directory, and then I'm going to use the same in 3 approaches. Okay, so let's talk about the first way. This is going to be the longest section of the talk because as we go through, I'm going to be describing more about like the nuts and bolts practicality of the very hand-wavy explanation I gave you with the picture at the beginning. And moreover, I will concentrate in the other parts of the talk on the differences from the object-oriented rather than just going through everything again. So bear with me on this. And unfortunately, there are about 3 concepts that I need to get through, and there's no good order for them. So you might just have to suspend a kind of like, well, what's that mean until I've got to the 3rd thing, and then hopefully it'll all fit together. And I welcome people putting questions. I'm keeping half an eye on the wee question box over there. So if you're completely lost, do let me know. The major components of any of the renderers actually is some way of storing that scene, some way of holding the objects, the spheres and the triangles, and walking through it looking for intersections. Some rendering process that's going to be keeping track of which pixel we're currently looking at. the thing that's going to do the radiance calculation, that's going to take essentially the rays that are going through the scene, the materials that are on the objects, and doing the intersection and saying, well, given this intersection point, where else might light have come from? There are the materials, and then there's just the mathsy part of doing the intersection itself. The way that I chose to do the scene in this object-oriented version is pretty familiar OO style. That is, I'm going to make a base class that's just a pure interface called primitive, and it's going to have one method only. Oh, sorry, I forgot. I'll go back to that. One virtual method only. So I'm going to have polymorphism. So my spheres and my triangles will be treated the same by the rest of the program. The rest of the program only cares about primitives, and the rest of the program is going to be calling this intersect method. The intersect method is going to say, does this ray that I'm giving you here, and I've not highlighted that one, let me use the mouse. This ray that I'm giving you, and a ray is a point and a direction. Does this ray intersect in any way with your primitive? And if it does, I would like to know the specifics of that intersection. Like, where does it hit, which is just a position in space, and the normal. We don't need to worry about normals, but the position in space and like the direction that that surface is facing. And then the material, which is a pointer in this instance to a particular implementation of something which we'll look at in a moment. And now some of you will probably be screaming and going, this is awful. How terrible could you write? How could you write this? Because this method, as you can see, is returning a bool, and yet I'm passing this intersection record by a reference. And the expectation here is that the method should return false if you missed, and return true and fill in the record if you intersected. And that's just a terrible, terrible anti-pattern that I regret, I'll be honest with you. But in my defense, I had made the decision that things like standard optional or any kind of optional thing sort of felt more functional. They're more over in the functional world. And so I sort of deliberately cut them off from myself. So I've kind of cut my nose off to spite my face here. I've got some unpleasant code here. But if I allowed myself to use all the things I would normally use in the OO land, then eventually I'd end up with just that blended C++ that we all actually write in, right? So that doesn't make for a good talk. So don't do this in your own code, but consider returning an optional if you wanted to say, is it intersecting or not? But because I'm not allowing myself to use these sort of functional ideas, I'm not going to here. The hit object automatically sort of, it starts itself up in a default unhit position. So there's nothing like uninitialized in that, for what it's worth. Then the render loop says, for all y, for all x, for all number of samples per pixel, so there's a lot of x by y by z kind of number of things that we're multiplying here, so this is why it takes so long, generate a random ray that passes through that point. The key here is it's random, right? And by random, it's perturbed so that, I know I said earlier when I said a line that goes through the eye and the pixel, it actually goes to a random point on the pixel. And in fact, it's also slightly bent up and down by the point on a where the lens would be of the virtual lens that we're simulating, which gives us depth of field for free as well. So, but the fact that we're randomly sampling and averaging out, we get these things for free. We get anti-aliasing and we get depth of field, which is nice. So we've got a random ray that passes through this particular pixel in some way, and then we're just going to ask some other system, what is the radiance that would come down that ray towards me? We give it a random number generator, don't worry about that. And we say 0 here, because this is going to be heavily recursive, right? At some point, the material that we hit is going to say, well, what radiance hits me? And we want to be able to stop it somewhere. So we give it 0 to say, you're the 0th level of the recursion. At some point, you probably want to give up. There's no light coming. And then we sum that into this accumulating color. And then ultimately, we plot the x and y with the color divided by these number of samples. And there you are, you have an image. Well, there's a lot of things we've got to talk about yet. So first of all is this radiance function. How do we know how much light is coming down some arbitrary ray in the scene? First of all, we say, have we recursed too much? Is this just, we've bounced around 100 times and we're never going to hit anything? If so, let's just assume that that we've lost all of the light energy. There's no light energy left to be worth tracking at this point. So beyond the maximum depth, we just stop and return vec3. Now, here I'm using vector3 to represent a color. Vector3 is actually just a tuple of doubles, and I use it for color here. And its default constructor is 0, 0, 0 or black. The next thing I do is I make this terrible mistake of putting an intersection record on the stack and then asking it to be filled in, but we've covered that. If the scene object says there is no intersection, then we've shot off into space. Our ray has missed everything in our scene and is currently off to Alpha Centauri, and as such is never going to hit anything. So again, we're going to say the radiance coming along that direction is 0. There is no radiance. Next, we say, well, I'm sort of told you a white lie from earlier. You know how I said I just picked a random direction? So having hit that sphere, you remember this picture here, I'm picking a random green direction and I'm just going along that direction. Well, that does work, and that's perfectly acceptable, and that's a much more traditional way of doing path tracing. It's more honest. But if you want to reduce the number of samples you need to throw into your scene to get a somewhat decent picture, you cheat. On the very first bounce, you have a special case where you say, okay, let's just do a few samples in generally a bunch of directions. And the way that I pick those bunch of directions is to use polar coordinates. And here the U and the V are the polar coordinates around and up. And what I'm going to be doing is I'm going to be sampling a random point around a sort of grid in polar coordinate space. So I kind of look in all directions around this hemisphere and say, well, let's look at all these places, and then we can average those out. On subsequent bounces, though, I only do one because it just runs out of, you run out of a CPU too quickly. But it's really just an optimization, and not an optimization in terms of speed, optimization in terms of getting an image that looks like anything sooner rather than later. And then we're into the sort of like the guts of it. We are now going to be picking that U and that V, which are this sample, which I'm counting between 0 and the number of samples we're doing, divided by the number of samples. So it's like a value between 0 and 1. And we add some amount of random noise into that on both axes. So we can perturb around the grid of polar coordinates that we're sampling. And then we also kind of roll a D20 here. We pick another random number. And that random number we're going to give to the material, because the material will need to do some random maths, which we'll see in a second. And you could argue that I could pass the random number generator into the material here, and it could ask for its own random number if it needed it, but this is how I chose to do it. We then tell the material, hey, what color would you be, please, given this parameterization of U and B and this D20 I've rolled for you. Now, of course, that material doesn't know how bright it would be unless it's a light. If that material is itself just intrinsically bright because it's a light, then it can just say, yes, I'm bright white. There's no need to do any further tracing. But that's not true of almost any material. Most materials, even if they have their own intrinsic brightness, they also reflect some light from the scene. And in order to work out what that light is that they're reflecting from the scene, they need to be able to go back out to the scene and say, well, how much light is coming into me? Now, at this point, we have kind of a circular dependency between the scene and the material, because the scene needs to find the materials in order to say, what color are you? And the material needs the scene in order to say, hey, can you intersect with and tell me what light is coming into me? And the way that I sort of broke this is by passing an interface that implements like sampling interface that I construct on the stack here, and I pass it into the material saying, if you need to sample more radiance coming in, you can ask this sampler to do it. And of course, the sampler really just asks the scene, except that it asks the scene with a one higher depth than before. That gives us the ability to, this is the thing that's going to cause the depth of increase as we do more and more recursive ray casts into the scene. Now, the recursion is sort of hidden here, but it gives the material the ability to do multiple samples if it wants to, or fewer samples if it doesn't need to do any samples at all. So there's a bit of a strange thing going on there, and we'll see how I broke that in some of the other slides later on for the other approaches, I should say. And then having summed up all of those samples in this sort of hemisphere that we're bouncing light around, looking for light coming in, we then give the material one last chance to say, well, also, regardless of what samples we did, are you just intrinsically bright here? You know, do you want to monkey in some way with the light that came in? And the material might choose to look at the direction and decide to perturb the color in some secondary way. It doesn't really matter at this point here, but that's just how the code is going. So that's the materials. So we've seen broadly how the scene fits together and how it iterates, or how it asks, sorry, we've seen how the renderer works and how it asks the scene to intersect, and then having found those intersection points, how it's going to sample back out and use the material to decide which colors things are going to be. We haven't looked at either how we intersect the scene or how the material makes the choice of which color it is. So we're going to look at those next. But first of those, we're going to look at the intersection. And this is the implementation of the primitive. If you remember, we have this base class primitive for spheres. And here, what the sphere is doing is it's marrying, sorry, what the sphere primitive is doing is it's marrying the math library that I wrote. Remember, I said there's a sort of math library that is general purpose. And that has its sort of Platonic idea of a sphere, which is just a point in the middle of the sphere and its radius or something equivalent. And so I tie together the ability to intersect physically with a sphere and the material that this particular primitive has. And then I implement the intersect interface. And I implement it pretty trivially. I ask the sphere, hey, did I hit you? Does this ray intersect you? And if not, we're finished. We can return false. If it did, then I need to do a bit of extra work here to tell whoever called me that the specifics of that intersection, where it hit and what material it had. And you can imagine the triangle one looking pretty similar. Here is the actual code for that sphere intersection. And the reason I'm going to go into this is not because I want to bore you with maths. It's just that there are some interesting things, and I was able to sneak in some functional programming things that make more sense in later on. I'm sorry, I'm confusing myself. The main thing is that when you're taking a ray and intersecting it with a sphere, you are solving a quadratic equation. And if you remember from maths, the quadratic equation has either no roots, one root, or two. And they correspond to the ray missing the sphere completely, the ray grazing the very, very tippy tip edge of the sphere, which essentially we might as well treat as a miss, or the ray going through the sphere and hitting it in 2 points, one on the near side to the sphere and one on the far side of the sphere, like putting a knitting needle through a balloon, kind of, well, the balloon would pop. Bad analogy, I'm sorry. So before we can work out whether there is what the two intersection points are, we calculate the determinant, which is the sort of b squared minus 4ac bit, if you remember. And before we can do the square root, we need to see if it's less than 0. And if it's less than 0, then there are no real roots. And what that really means is that our ray misses the sphere. So we can say no hit here. Otherwise, we take the square root, we do some more maths, and then we can populate the hit with a whole bunch of other stuff, which again, I've elided just for clarity in this slide here. Okay. Oh, I've got things. The triangle is more complicated, and we'll get into that a little bit later on. Now looking at our materials, this is what the base class for materials look like. Again, because this is the object-oriented view, rather than parameterize the materials and have a general purpose material system, I decided to have a base class and just be able to ask the material to sample at a particular point. And we give it the hit record, we give it the ray that was coming into this particular point on the material. We hand it this sampler, which allows it, again, to go off to the scene and say, well, I'd like to find out what light is coming into me. And then here are the 3 parameters that we talked about, those polar coordinates for a sample point that we would like it to make, and the random p value, which is a dice roll. And then an example of a material would be this shiny material. And those who know much about how, or have looked into computer graphics before, things that are shiny, we typically model as a combination of some amount of reflection. And if you can just in your mind's eye picture a shiny apple, so you've got a shiny red apple, the classical cartoon like highlight on the apple is actually the color of the light. So if there's a light above you, you'll see like a white highlight on the apple, which corresponds to the light from the light bouncing directly off the apple and coming to you, unmolested by the color of the apple, right? The highlight is not red on a red apple, the shiny part. So that's called the specular part, and that's to do with the reflection component. And then the second component is a diffuse component, which is more to do with just the general lighting of the apple. And that's what makes the apple red. And it makes the apple sort of slightly brighter red facing the light and obviously darker under the bottom of the apple. And now in a traditional rendering system, you actually model those completely separately and then you add them together. Sorry for my pop-ups there, I thought I'd turn those off. But because we're doing so many samples, instead of tracing two separate rays, one for the shiny part and one for the diffuse part, we're going to look at that dice roll. And we're going to use the random number p here and say, if that value was less than our reflectivity, then hey, today is your lucky day, shiny part of my material. We're just going to follow the path of the light that bounced directly off. And so we use a cone sample to generate the next ray. And the cone sample will take the incoming ray position, bounce it, and then pick, depending on how shiny or otherwise we are, a cone-sized area to sample over. And we return the color directly that sample gives us. We don't modulate it in any way with the color of our own material. We just say, hey, if a reflection, that's the color you get. If, however, the random number is greater than or equal to the reflectivity, then we're going to model the diffuseness, in which case we're going to take our own diffuse color and multiply it by another hemisphere sample. So this is just another thing, just like the first bounce, where we'll just sample over that hemisphere and we're looking for light coming basically from any direction. And the way that this works is that there are going to be enough samples bouncing around inside our system that the law of large numbers means that the more shiny it is, the more of those will hit the first path, and the less shiny it is, the more will hit the second path. And when we average them all out, it all comes out in the wash. So we get away with a lot of things, complexity, just by saying, well, we just do enough samples and eventually it'll come to, it'll all work out. Oh, and I've got highlights that I forgot about. And here are the results. This was rendered by my code, but the scene is my friend's. It just looks really pretty. Like we can see that the yellow ball in the background here is blurry because it's out of focus. It's too far away. The black light here, black sphere is very, very, very reflective. And so we can see all these different highlights going on in the scene. It's just really rewarding to see these things happen and sort of come as a natural occurrence of the program. So again, cool. It's nice to do these kinds of things. It's nice to have a project that generates nice things rather than just an executable. What did I like about this approach? Well, the layout was really super familiar to me because, as I say, I'm naturally an object-oriented programmer. Testability was top-notch, partly, again, because I naturally write object-oriented code, and so I kind of know the techniques and tools. But you saw those virtual methods. They're just great seams to put some kind of edge around parts of my system and say, hey, I can test the scene in isolation. Hey, I can test a material in isolation. You saw how I was aggregating the math sphere object with the sphere primitive. So I could separate, again, the concern of, are you in a scene, participating in a scene, from these pure maths of like, where did you hit the sphere? So that was great. It was really testable. And the performance was pretty good, actually, despite all those virtual calls, which normally my alarms are going off. It did a good job. And we'll talk at the end about how all the performances fit together. What didn't I like? Well, I think I've labeled this one already. The stood optional thing was probably a mistake, because even reasonable object-oriented folks would use standard optional, right? And I think I probably overused virtual. I used, the material could have just been parameterized. There weren't that many types of material. Perhaps I shouldn't have done it that way. But again, this is a caricature. I'm trying to show the extremes. And also I was aware that if I didn't do some of these things, then by far the 00 version would win out, just because I'm more used to writing the code that way. Let's talk about the second approach, functional. This scene is showing like the difference between the shininess parameter and some of the other parameters that you can give the materials. That's quite sweet. So in the functional programming, I did have access most recently to GCC 11. I finally got it building with GCC 11, but I couldn't get enough working to be able to use standard ranges. So I'm using ranges v3, which I consider to be like a tenet of functionality, building up and processing and transforming using pure functions a set of data as it flows through a range pipeline. So we'll see that in a second. And then I made a sort of controversial choice here. Rather than using standard optional, I used Cybrand's TL optional, which has a number of more traditionally FPE, at least in my eyes, features like mapping and transforming on optional variables, which is useful, and we'll see it very shortly. So it's not even standard optional. I know I was bemoaning the fact that I didn't have standard optional before. I'm not even using standard optional in the function program. I'm using something more functional than standard optional. Excuse me. So the scene, I decided to use simple structures to hold either a triangle primitive or a sphere primitive. And you can see that I've literally taken the same kind of object, a triangle and a sphere and a material, and just put them in a structure together. And then the way that I'm achieving polymorphism in the scene is to have an array of these primitives where the primitive is a variant. So the variant is either a triangle or a sphere, but there's no virtualness here. There's no indirection through a pointer, which is kind of neat and cute. And we'll see how we use it in a second. Now we're on to the real cool stuff. Maybe too cool. Maybe too cool. So I've just seen a private message that I shouldn't have read just now. What I've done here is I've created an array output class, which is essentially a thin wrapper over a standard vector. This is going to hold all the different colors of the pixels as they're being assembled. And it can be constructed just with width and height, but it can also be constructed with width, height, and then a range. And then it will auto initialize itself by just iterating over the range and putting the values that it receives from the range into the width by height pixels that it's got. And so what I'm doing is I'm passing in a view in the ranges, which generates essentially all possible combinations of between 0 and height and 0 and width, Cartesian product. So for all height, for all width, it will generate a tuple, y comma x, and it will pass that to the function render 1 pixel, and whatever that returns is whatever the iterator that we get from this pipeline is going to return. And so what we're doing is lazily generating an array of vector 3s, as this will return up here. And as we're generating and iterating over that array, we're writing it into the output. So it's kind of a neat way of getting like an iteration over something. I'm maybe too cute. And again, I'm probably like a kid with a new toy. I'm like using everything I found in Rages, and perhaps I shouldn't have done it. So this render 1 pixel is the function that's going to be called for every height, for every integer between 0 and height, and for every integer between 0 and width. Those will be passed as a tuple, which I unpack here as y comma x. And then I'm going to go off to the scene and say, hey, please go and render the radiance coming in from that particular direction. I have a bit of a confession here. I tied myself in knots trying to find the right level of functional purity, and having essentially a global random number generator, which is what, it wasn't global, it wasn't the stack, but what the other system had, the OO system had, seemed not functional enough. So I construct one for every pixel, and then each pixel only mutates its own random number generator. It is as a nod towards purism, but those who know functional programming probably will tell me that I'm still doing it wrong, and it has a terrible performance characteristic too, which we'll talk at the end. Here is what that radiance function looks like. So this is the body of the radiance function. I couldn't fit the sort of beginning and the end of the function on the slide, but effectively we find a point of intersection, which is not on this slide. And then for that intersection point, remember we had those num-u samples, num-v samples that we did before. I'm using that same Cartesian product trick to generate all possible pairs of 0 to num-v, all possible pairs of 0 to num-v, 0 to num-u samples. I'm transforming that integer pair into the equivalent directional pair that I need to make it a polar coordinate. And then I'm passing that on to a function radiance at intersection. This is the bit that's going to be doing the material calculation. In this FP world, I have parameterized the material. There is only one function that does all of the material stuff. There's no polymorphism in the material side. And again, that function will need to say what all light is coming in to this intersection point, right? We need another way to call back in. If you remember, that's how, in the object-oriented version, we use an interface to essentially allow a phone home to get more radiance. Here, I'm passing in a lambda. So I have this lambda radiance for ray at the top here, and that's the function that's being passed into radiance at intersection. And it's essentially if you need more radiance, call this. And again, it sort of curries in all the various parameters, except it also curries in depth +1, so that we do eventually terminate the recursion. Oh yeah, sorry. And finally, this whole range here, this lazy range, is going to be accumulated to sum it up, starting with an empty vector 3. So effectively, we just add up all those U samples and V samples. And I think it should be divided by the number of samples in total, which I've obviously missed off of this slide code. You know what it's like. Here's the radiance at intersection function. It takes the radiance function. So this is where we get our phone home. This should look sort of somewhat familiar to you. It's the ray, the U and the V parameterization, and this random number P. This is broadly the same as the previous code, with the exception of when I needed to get more radiance, I call that radiance func. Now, the cool thing about this is there's no virtual function to go through here. Whereas before, in the OO approach, I had laundered the connection between the scene and the material by passing it through a virtual function. Here, I'm actually passing a reference to the actual implementation of that function, which means that in theory, the compiler can go nuts here and do all sorts of clever inlining. Intersection was a lot easier than I thought it was going to be. If you remember, our scene is made up of an array, a vector actually, of those primitives, each of which is a variant of either a sphere primitive or a triangle primitive. But it just so happens that there's the similar layout between those primitives. Be it sphere or triangle primitive, it always has a dot shape, which is something that I can call intersect on, and it always has a material, which is a material. So I can use this template visitor to visit any type of primitive, prim_t, and save myself the trouble of having to write one for spheres and one for triangles. So that was a nice find. The other thing here is we're starting to see usage of the TL optional versus the real standard optional. The intersection code here, this primitive.shape.intersect, returns an optional hit, a TL optional hit object, rather than a bool and filling in all that horrible stuff. What size optional allows us to do is to call methods on an optional, like map, to convert it from one type to another, except that that method is defined such that if the optional is empty, then the emptiness is kind of just passed through, right? This function won't be called if it was empty, but an empty type of whatever this function would have returned is instead returned. So that saves me from doing an if check and having two different code paths. If this intersection is empty, then nothing happens. But if it isn't empty, if there is actually something populated in that optional, then it's passed here and we convert it into an intersection record. So that's kind of a powerful thing. You'll see more of it on the next slide, if I remember right. Oh, and I've just forgotten again my highlights. So this is where I go to town on this optional idea. If you remember, we're intersecting a sphere here. And what I sort of hand waved over before is we're solving that b squared minus 4ac thing. So here's the determinant that we created. And I have invented a new function called safe square root. And the return type of safe square root is optional double. Optional as in size optional double. If the determinant, if the value we're taking a square root of is positive, then I return an optional of the square root. If it's negative, I return an empty optional. So it's kind of a nice way of getting a square root without having to remember that you have to check to see whether it was negative in the first place, or exceptions, or all those kinds of things. So the thing that we do after the safe square root is we can say, well, what about we convert it and do the next stage of the equation, which I didn't show before. And so what this thing does is it's determining whether it's that grazing angle where you've only got one root. I have elided the code here, but this can potentially say, no, we still didn't hit. You know, although it was positive, it was so small that I decided that it didn't actually for numerical reasons, I don't want to treat it as a hit. So in which case I can return null optional. Otherwise, the job of this is to determine which of the two intersections is the correct intersection based on whether or not you hit the front of the sphere or you're in the sphere pointing outwards. So we return yet another optional double. And then finally, we map that towards a hit. And again, this map will be either an optional of the filled-in hit in the case that the optional returned by the previous step is in fact not empty, or it will just be an empty optional of hit if in fact that wasn't populated. So it kind of, the fullness of the optional flows naturally through here. And the reason this is a map and this is an and then is because in this instance, I have to be able to also say, no, we're empty now. I have to be able to null it out. This works in terms of optionals, whereas this works in terms of actual T's. I'm sorry if that's a bit vague. Hopefully, if you've got questions, you can either look at the slides or you can ask me afterwards and I can try a bit better to explain, but I'm conscious of time actually. And I'm also conscious that I'm not pressing the button to advance my highlights. So that's the end of the functional thing. We did a whole bunch of rather interesting range-based work, and we used a bunch of optionals to hopefully make things clearer in the sort of the happy path, with the unhappy path of something being either negative or missing, just naturally falling out of the flow of the and thens and the maps. What did I like about it? Well, mostly because I was in a functional mindset, I started putting const on everything I possibly could. You know, immutability and sort of value typing is something that functional makes me think of. And of course, I can do this. In any other of the code that I write, right? But it just made me think about it more, and that's a good thing. I could probably have put const expr on a lot of things too, but I didn't. There's an argument that the code is clearer. If you think in a particular way, if you see things in terms of a logical sequence of events, you know, like that intersection, you know, this and then this and then this and then this, where there's an opportunity for it to bail out and return an empty optional, which kind of is hidden, but implied by the structure, maybe that's clearer for you. The range stuff, I think probably was too cute by half, but it worked and it was interesting. And the testability was still good. Anytime that I wanted to insert a seam to test, for example, like the sampling, I could actually, in my test harness, instantiate a completely different function to sort of fake out a sampler and pass it in as that template parameter. You remember the radiance at intersection took a template parameter of like, hey, call this function if you need more radiance. And that allowed me to sort of puppeteer it and drive it and test the edge cases, which was great. What didn't I like? Well, the bane of anyone who deals with a sort of somewhat novel library that's very heavy on templates. The compiler errors were very cryptic, and I mean very cryptic. A lot of the time when you pipe one transform into another, if you get something slightly wrong, then the poor sort of template inference rules break down and the error messages seem to be unrelated to your original problem. Maybe that's just my lack of ability of understanding these things. So that wasn't great. If you've got concepts in your compiler and you can enable concepts, then using ranges with concepts gives you a slightly better ride. But I have a caveat with that, which is that you go, in some cases, you can go from a cryptic 3,000 lines of template error message to, oh, you don't conform to this concept. And that's maybe more helpful. But in one case, I had an iterator that I'd written, a custom iterator I'd written myself that was part of that packaging in the array output. And I hadn't quite modeled an iterator correctly. And of course, that's what the error message was. It's like, well, I wanted an iterator and you didn't give me an iterator. I'm like, but I'm pretty sure I did give you an iterator. Like I've written all the methods, I've copy pasted all the things from Stack Overflow that say, these are what an iterator should look like. And he goes, but it's not an iterator. And I was stuck then. And I had to actually dig into the implementation of like how it asserts whether or not my concept is an iterator. And it's like, well, it's either, it must be this and this and this and this. And then I would static assert each of those individually. And then one of them would fail. And I'd go, well, okay, it's not this then. Okay, and I copy through that. And so eventually you find the thing that you aren't, which then tells you why you're not an iterator. And it's because, oh, this particular plus plus operator wasn't const. And you go, ah, I wasn't an iterator after all. So I'm sure things will improve as time goes on, but that was my experience. Sorry, that was a real digression. What did I like? The performance was not as good as I thought it would be, especially given some of those inlineability opportunities. I probably can blame it on that standard random number generator that I instantiate per pixel. It's quite heavyweight to make one of those things and to pass it around. And I think probably I could have done without doing that, because I think I'm probably in the situation where I am neither functionally pure, nor fully taking advantage of, well, if you're not going to be functionally pure, you might as well use a global variable or a shared variable. So I could have probably done better there, and I could have easily have done some tests as well around the performance, but I haven't had a chance to do that. Let's talk about data-oriented design. This was the one I was really waiting for. Those other two ways were kind of by way of whetting my appetite and proving out the approach. I was really excited about what would happen if I was allowed to roll my sleeves up and get really down and dirty with thinking about how to structure everything to be fast. What data-oriented design says is that you should design around the most common operations. And then you design your data by the access pattern. So the theory here is that you're going to be dominated by the speed of RAM. And so if you can read through your data in a cache-friendly way, then everything is going to flow faster from that, right? If you're limited by RAM speed, then trying to get everything cache efficient is the best thing. Another thing that you should do is to avoid branches where possible, especially in critical bits of code. So come up with other ways of dealing with data. And in this instance, it means, like, instead of having an if check in the guts of your loop. So imagine you have all these different types of object in your scene list. And what you're doing is each time you're saying, hey, are you a triangle or a sphere? And then the next one you're saying, are you a triangle or a sphere? And the next one you're saying, are you a triangle or a sphere? That's kind of expensive. However you phrase that, be it through the variant or through a different virtual pointer. How about you just have a big list of all the triangles, and then you have a big list of all the spheres, and then you don't have to ask the question at all. And so that's the kind of thing we mean by avoiding branches and doing polymorphism by separation. Excuse me. What changes did I make to the core algorithm? Well, intersection is by far the most common operation, like hands down. All we essentially do all the time is take rays, intersect them with triangles and spheres. Everything else is just line noise compared to that, the performance impact of that. So we should really optimize for that case. And once we start thinking hard about that and looking at what the code is doing, you might realize that in the lovely OOE world of, like, saying, here's a ray, tell me about the intersection or not with you, Mr. Sphere. You've already done a whole bunch of calculations that you probably don't need, because if you did hit the sphere, you've now returned how far away the hit was, the normal of the sphere at that point, the material, a whole bunch of things that maybe you didn't need, because ultimately we're going to be looking for the nearest intersection only. When we're casting a ray through the scene, we're going to say, what do we hit? And it's the nearest one of those that's the one that's important to us. So I already spoke about this other stuff here, that we've only got two types of objects, so we're just going to separate them into all the triangles and all the spheres. And even within that separation, we can separate the data further. So it turns out that when you're doing a triangle ray intersection, the only thing you actually need in order to determine if the ray passes through that triangle are the three vertices at the corners of that triangle. And so I'm going to take them and put them in their own array, because for the most part, I'm not going to be colliding with any one of those triangles. As I run through my 1,000 triangles, I'm not really expecting many of them to be a hit. So why would I waste my cache with things like the normals and the materials of those triangles if I don't need them? And so that's what I've done here. I've separated those triangle vertices structures there are literally just X, Y, and Z of, three lots of X, Y, and Z, one for each corner. Now I have triangle normals and I have triangle materials. And the sort of awkward thing about this is that now I need to be really sure that there's the same number of vertices as there are normals as there are materials. It's really easy to get those things wrong if you're not very careful. Whereas if you just had a vector of triangles, like I did in other cases, you can't ever get out of step. And it's never the case that the 0th vertice has the wrong normals or materials associated with it. So you have to be careful. You have to do your housekeeping right. Spheres, similarly, yeah, this is right. Someone has put in the chat here, this is like the difference between array of structures and structure of arrays. And this is a structure of arrays where we separated out some of the data. And And it's a sort of classic trade-off between the two. And we'll talk a bit about that at the end of the performance impacts. So in the case of spheres, it made sense to just separate the sphere, platonic ideal object, and the material. There's nothing else that I didn't need inside the sphere object. So what does this look like? So this is what the intersection code looks like for all the spheres. So first of all, I've essentially manually inlined the code that would have run before around the, I guess I haven't manually inlined it. What am I talking about? Sorry, excuse me there. I just didn't show it for the other pieces of code, the other approaches, the scene intersection. But this is the part of the scene intersection that works specifically with spheres. So first of all, we have to do another ugly thing where we count from 0 to the number of spheres. I can't use my nice range for here because I actually need to know the index, because that index is going to help me index into the material array that is associated with this sphere. We do the maths. If we didn't hit, we continue. So this is already showing the glimmer of where the performance comes from in this instance. For the most part, most rays don't hit anything, or if they do, they hit one thing in the whole scene. And so we're spending most of our time just counting through the spheres, doing a tiny bit of maths and saying, oh, it didn't hit, go around again. So you can imagine that the CPU is spinning in this loop as tight as possible. All the lovely caches, the CPU caches, the instruction caches are all hot and beautiful. The maths is flowing well. Oh, delightful. And hopefully the branch predictor is clever enough to notice that we basically always continue here. And so we're in heaven. We're going as fast as we can. Oh dear, we actually hit a sphere. What a shame. What are we going to do? Well, we'll say, is it nearer than the current nearest hit? And if it is, all we're going to do is remember which index it was and how far away that was. And then we get on with our lives, carrying on through the rest of the sphere. So again, we still haven't done very much work, even when we have hit something. If we didn't hit anything, we can say the spheres didn't hit. Otherwise, now we can actually just do the maths, the one-time maths for that one intersection of the one sphere that's guaranteed to be the nearest one. We can work out whether we're inside the sphere, outside the sphere. We can work out the normal. We can work out all the other bits and pieces we need to do in order to populate this hit object here and look up the sphere material. So this is the first and only time we actually look at the material array. So this is marvelous, marvelous. And again, I forget that my little thingy has got highlights. And then the same thing for the triangles, right? The triangles looks broadly the same. For all the triangles, we're going to calculate U and V. U and V are different U and V from the ones that you saw on the sphere and the thingamajig, the hemisphere and polar coordinate stuff. U and V in this instance are a parameterization across the triangle itself. And we just happen to know that you can calculate the intersection of the ray and the plane that the triangle is on. And then we can say, well, how far in U and V terms are you from the bottom left-hand corner of the triangle? And it just so happens that if you're less than 0, then you're below the triangle. And if you're greater than 1, you're off the top of the triangle in one axis. And likewise for the V here. And then to deal with the fact that the triangle actually has a diagonal across it, you look at U plus V. So anyway, a tiny bit of maths here. And the vast majority of ray triangle intersections are going to be either way off the bottom of the triangle or way off the top of the triangle. And so we're going to spend our entire time in these 3 lines. And then we have the same trick. If we pass the U test, we pass the V test, we calculate the distance, we work out then if it's the nearer one, and then only at the end do we do the work to generate the normals and all the other work that needs to be done here. So this is absolutely splendid. This is going to go like fire. And again, I should remember. The rest of it is broadly the same. I'm not going to bore you with all the various material things. They are essentially the same. What did I like about this approach? Well, it was so much fun. It was so much fun because I could really suspend all my normal, like, good programming practices. Good. I'm going to put air quotes around good because obviously good is in the eye of the beholder, and this is not bad code. It's just different code. But I could suspend everything in the goal of being super performant. And so it was great fun to optimize it, and the performance was good, with a really big caveat, which will suddenly record scratch us into the second, I won't say half of this talk, but I will say the other part of this talk, which was the unexpected pleasure at the end of finding all this stuff. So let's go and round off the things I didn't like. I didn't like how tricky it was to test. It wasn't impossible to test at all, but I was back to sort of almost integration style testing because everything's kind of in one place, right? There's this big old scene, and the only way I can test the intersection is to just throw triangles into the scene and then say, hey, scene, did you intersect? And he goes, yes, I did. I'm like, great. I can't get in, because all of those seams that I use in OO or functional are deliberately not there, and they're in fact blurred on purpose for performance reasons, which is great, right? But it was a bit harder, and I'm sure some of the folks on this call who do this more day in, day out can say, no, there are tricks for this, and I'm sure there are, in which case, you know, I just need to learn. Also, I noticed that, and this is perhaps just my OO roots showing, if I wanted to change it, so if I wanted to add, say, a new primitive, there are a number of places in the code I would have had to have edited. There's the place where the scene's set up and all the various arrays that then constitute like the guts of whatever new object I'm adding to the scene, multiple arrays of them. There's all the management of that, making sure they're all kept in step. And then I'd have to go and edit the other part, which is like the rendering part, to say, well, this is how I'm going to teach you how to render this thing. And it's just like good old fashioned, I guess, C code before I thought, you know, OOE, where the code is littered around the code base. And there's a little bit of that in functional, where the visitor sort of in some way contributes to the behavior of the object you're visiting. In OO world, of course, I would just literally make, you know, cube.hpp and cube.cpp, make it implement the interface, and then no one else need know that my cube even exists. It just works, and that's kind of a nice property. But I'm probably just grumbling like an old OO person. Conclusions then. Oh, and Kate's put something about GPU stuff with arrays of all the X's, all the Y's, all the Z's. Yeah, yes, absolutely. There's lots of cool things that you can do with those kinds of things. But very entry level stuff here. So in conclusion, my favorite, well, there's no surprise here. The thing that makes C++ so excellent is that you can pick and choose and mix and match within the same file, if not even with, you know, the same project at least, you know, you can have bits of the code base that pick the best of all worlds. You know, I've artificially limited myself to a silly subset in all three cases. Realistically speaking, if I were to have my druthers and do this over again and write like the one true renderer, I would probably use more functional code in my OO style. And then I would have probably a mesh class that holds a whole bunch of triangles that I do then use a data-oriented design to run through to find the intersection with. And I mean, another thing I should have said right at the beginning is that anyone who's actually written any kind of rendering code will note the absence of any kind of bounding volume hierarchies. That was definitely on purpose to prove a point about the performance stuff. So that would also, in any sensible system, you would have a hierarchy of like, here's a big sphere. If you don't intersect with the big sphere, I know you don't intersect with anything that's inside the big sphere. So I can kind of cull large areas of the graph at once. Someone's asked me, have you ever had an add-in edge cases at the end defeats all my optimization work? Not as such in this particular example, but I have, yes. I mean, very often in general with optimization, in my experiences, the best thing to do is to try and make it so that the good case works, and in the bad case, you can at least detect, even late sometimes, and kind of go, well, I did 100 things, and I discovered that actually one of them was nan, and now nans are all the way through my calculation. I'll just have to go and redo those, and that's probably sometimes worth doing as a sort of post process. But I won't go into specifics now. We can talk in the questions at the end. Otherwise, I will be here forever. So I can't not. It wouldn't be a me talk if I didn't talk about the actual performance and we didn't show some assembly code. So, you know, there's no compiler explorer link, but there is some assembly. So the performance here I measured on my desktop machine here, which is a lovely 3 gigahertz Intel machine, sort of Skylake AVX 512. I was using GCC 9.3 at the time, and I've turned on all the governors so that, you know, I'm running my electricity bill up ridiculously. And these are single threaded as well. I can run with multiple threads and do some clever things with that, but this is just more interesting just to look at the single threaded performance. So to give you an idea about how ridiculously slow this whole endeavor is, to render a 256 by 256 image that looks grainy as heck, like this one on the right, this is not a rendering artifact on your side. This is not a video artifact. This is actually what it looks like. In fact, it's probably kinder to have thrown it through the JPEG system. This is 32 samples per pixel, and this scene only has one sphere and 38 triangles. It takes over a minute. 72 seconds for functional, sorry, 72 seconds for object-oriented, 73 for functional, so those are basically the same. And the data-oriented is pleasantly faster, which was nice. That's what I was expecting, right? You know, a little bit faster on the data-oriented. Still takes a minute though, crikey. So yeah, you can only imagine how long it took me to render all the other images that I've actually been showing you that look nice. This scene, this is an owl scene. This was done at 128 samples per pixel. The parameters were tweaked just to be around about a minute and a bit. Otherwise, life's too short to run all of the benchmarks. This has 100 spheres and 12 triangles. And, you know, with the previous scene, hang on, let me make sure I press the right button here, there's only 38 triangles and 1 sphere. So even if the object-oriented and the functional are jumping all around RAM to find their data, it's still probably going to fit in the L1 or L2 cache. So there's not going to be a huge difference between that and data-oriented from the RAM point of view. With 100 spheres, we know we're starting to put a little bit more pressure on it, but not really enough. But, and again, we can see that the object-oriented takes 96 seconds, 113 for the functional. That's disappointing. That's probably, again, that random number generator that's hidden in there somewhere that I shouldn't be doing the way that I'm doing. And the data-oriented is a pleasant 64. In fact, surprisingly identical to the previous run. And I had to do several checks because if you've ever done performance work, you will know how important it is to keep like a literal diary of what you're doing. I have a Word document or equivalent, you know, Google Doc open. I'm typing notes all the time so I can look back and say, did I run that with or without the thing? Oh, yeah. And so I can go back and check my working. Or better still, you write a script to run it all unequivocally the way that you mean it to be done. Anyway, aside over. This is the Suzanne monkey scene. This has 970 triangles, which is starting to get into the more taxing for the caches sets, but should be much more grist for the data-oriented mill. And here it takes, you know, 96 seconds, 150, disappointingly long in the functional. And then suddenly the data-oriented took a massive, massive hit. You know, this has been 2/3 the time of the other two at least. And now suddenly it's in between the two. What on earth happened here? When I first gave this presentation, I had to stop the presentation here because I didn't know what was going on. And it was like, and there you go, hooray. And then thankfully, I've had the time to work out what happened. But what did happen here? What happened? I mean, this is the short version because we're running low-ish on time. I used the perf tool on Linux, which records a whole bunch of useful performance metrics and counters that are physically on the CPU, that actually count the number of little things that the CPU is doing, how many instructions, how many cache hits, how many cache misses. And I've boiled it down to the things that matter on this screen. So those of you who know, you know, have already looked at the bottom, you know, I generally try not to put too much information on the slide and then talk about it because everybody and their dog has already gone down to this line and gone, oh, but I'm going to talk about them. So this is amazing. You know, the first object-oriented one is getting nearly 3 instructions per cycle are retiring. That's amazing. Just amazing how clever CPUs are these days. We did 23 billion branches and only 139 million times did the machine make a mistake and go the wrong way. That's 0.6%. That's frankly, I'll take lottery odds like that if you don't mind. You know, maybe we can get the branch predictor to predict the lottery odds if we work out the right sequence of jumps. The functional, well, it doesn't get quite as much. You know, this is not as many instructions per cycle, so that's not as good. That means it's spending its time waiting for results or waiting for various things to happen. And the thing that it's waiting for in this instance is the branch predictor, which is getting it wrong 5% of the time, which is remarkably high for any program. But if we come down to the data-oriented design, if you can see that 12%, that is like, you know, more than 1 in 10 branches in the whole program are being mispredicted, you know there's something weird going on. 12% of branches. Now, I'm going to do a super quick overview of the branch predictor for those who are going, what's the branch predictor? The branch predictor tries to make an intelligent guess as to which way the program flow is going to go before the CPU has actually executed the instructions that will tell it which way the flow is going to go. The reason this is important is that much like a production line, you have to pre-order a lot of stuff. There's a lot of steps that happen inside the CPU, number of cycles that have to go. You have to fetch from memory the instructions you're going to execute. They have to be decoded. They have to be scheduled. All these things have to happen to the instructions before they finally get to this stage where they can be executed. And so if every time you got to a branch, you stopped going, well, I don't know if we're going to go left or right here. Let's just stop. Then you would waste a lot of the opportunity you could have of just guessing which way. Okay, well, let's just assume we're going left, right? Until we find out, oh, no, it wasn't left. Everyone back. Okay, we'll go down the right four. But if you got it right, you're like, hey, this is great. We're already most of the way down the left branch. So the branch predictor is given the unenviable task of taking an arbitrary piece of my code or your code or the operating system's code and trying to make sense with literally no context of what your program is doing and make a decent prediction. And it's doing this in hardware at 4 gigahertz or 3 gigahertz. It's amazing. Hardware engineers, honestly. Cutting to the chase, it was pretty obvious once I said to Perf, show me the lines of code that are causing the problem. And it turns out that 44% of the time, this jump here, this JA, which is a jump if above, was being mispredicted. So what happens is that when a misprediction event happens and Perf records it, it says, well, where did this come from? And by the time Perf looks at where it came from, it's actually seen the result of the mistaken branch. So in the case of a jump like this, a jump if above, there are 2 possible destinations for this instruction. One is that the jump is taken and the processor goes from here over to 350 down here. The other is the jump is not taken and it just carries on to the next instruction. This number in the left-hand side here is the percentage of time that the misprediction event happened when we were on this particular instruction. And it's a percentage of the overall program. This is not local, this is the whole program. And you can see that essentially 44% of all the branches that fell through this jump, that is, it was not above, and so it went to the next line, were mispredicted. You know, that's almost coin toss odds, right? 50, you'd think if you just guess randomly, you get 50% here, and it's getting 44%. And if we look down at the destination, that means that every time it predicted that it did jump, it was wrong 46% of the time. So 46 plus 44% of the time are accounted in this one jump alone. The branch predictor is getting it wrong almost every time, or at least no better or worse than flipping a coin, which is terrible, terrible. What is that code? What are we looking at here? This is inside the triangle intersection tester. Now, if you remember, I glossed over this before. I'm going to gloss over it even more here, and hand wave a little more. The code broadly is do something, calculate the U parameterization. If it's less than 0 or more than 1, then as I said, it's off the top of the triangle, off the bottom of the triangle in sort of triangle units. Calculate V if it's off the bottom, or sorry, off the left of the triangle, or if it's off the diagonal, then can finish. Else, go off and do triangle things. That bit that's highlighted on the left, the U is less than 0 or U is greater than 1, compiled into the very instructions that we saw. This JA skip is the one that was mispredicted, and the V commas D is the next line. This is a compare. So it's saying compare XMM0, can't read. It's compare XMM14, which just happens to have been loaded with the constant 0. Compare it with U. If it's above that, go to skip. That's the continue happening. Otherwise, compare U with a memory address that contains the double precision value 1. And if it's above that, skip. So this is, this is a pretty standard, sensible way to do an OR condition here. If it's less than that, skip. Else, if it's greater than that, skip. Brilliant. Except, and this is the insight, almost no ray, any one ray is very unlikely to intersect with a triangle, any one other triangle, right? For the vast majority of ray triangle intersections end in a miss. But any random ray is definitely going to intersect with the plane of the triangle somewhere. And it intersects with it in essentially a random spot, right? It could be off 1,000,000 units off the top, or 500,000 off the bottom, or 1,000,000,000,000 off to the, there's just literally the only place where it intersects with the triangle is where the U is between 0 and 1, but U is essentially a really, really, really random number. So that means that the result of is U less than 0 for any random number U is totally unpredictable. The result of if U is greater than 1 is similarly unpredictable. The result of is U less than 0 or is U greater than 1, like combined together, should be predictable. That is, we should predict that it's like always the case, because it's vanishingly rare that our ray happens to actually intersect with the triangle. It's like, very, very, very infrequently. And frankly, I'll take a misprediction when that happens, and I'd rather the branch predictor predict that it's not and just loop round to the next triangle. And even more so, like the whole combined thing of u is less than 0 or u is greater than 1 or the v, it should be even more predictable, because again, that just doesn't happen. But the problem here is that the compiler doesn't know that u is less than 0 is unpredictable and u is greater than 1 is unpredictable, but the combined thingamajig is predictable, and it will generate the two comparisons and the two branches, each of which individually is unpredictable. I have found a trick that sometimes works, and that is to do something pretty egregious by saying, instead of using a logical OR, use a bitwise OR. And so I'm taking the u is less than 0 and turning it into a value either 0 or 1, and then I'm bitwise ORing it with u is greater than 1, and so on. And sometimes, and I'm saying sometimes because the second time I gave this talk, I thought this was the solution, and it turns out I was wrong again. Sometimes that coerces the compiler into combining those two checks into one check, or doing the two checks and combining them and then branching. And that makes a big difference, as we'll see. So in this particular instance, it happened to work, right? I converted the code on the left-hand side into the giveaway. I thought there were highlights. The indefensible should never pass code review except under the most extreme conditions, with the biggest explanatory apologetic comment above it and tests that check that it still works and all that stuff, none of which I actually did in my case, which is mea culpa, because when I came to redo this talk, I realized that things had moved on in compilers and it changed. So, whatever. But this thing over here where I'm doing a bitwise OR was enough to cause it to combine them into one comparison and a CMOV, which set a flag, and another comparison and another CMOS. So now I've got two flags, and then it would OR them together and it would have one jump. And the difference is 35% speed. So suddenly making that one line change, literally deleting effectively the second pipe character of the OR, makes it go 35% faster, which was mind blowing. And again, I had to go back and kind of go, am I just measuring the wrong thing here? Okay, I copied the code onto a different computer and see if it works there. Oh, it still works there. I'm going to run it under perf and run the branch predictor, because these type of things, extraordinary claims require extraordinary evidence. I had to go and find a whole bunch of things to back up my case here. So it was a lot of fun, but very frustrating. The final statistics then, when I went back and I backported, or I thought I had backported that check into all of the other code paths, it sped up most of the other things too, and it brought some of the worst cases of the functional programming down too. So, we've got down from 72 seconds to 64. So everyone's kind of agreed that the Cornell C, being super simple and presumably extremely predictable, even for the virtual calls, is basically the same between OO and DOD. The OWL basically got a little bit slower. It's the same in FP. It's the same in DOD, because for whatever reason, the OWL's basically made out of spheres, and the spheres didn't seem to have the same problem. It's the triangle code that had the biggest problem. Suzanne got slower, and I still am not 100% sure why. There's a footnote there, and I spent up until about 2 a.m. this morning trying to find out why, and I gave up and thought, well, hopefully you'll give me the benefit of the doubt. It sped the FB up and it made this big speed up on the DoD. So I did get to show you some assembly. I did get to talk about C++. I did get to explain my caricature of ideas, and I did get to, hopefully, to get across the point that, first of all, it's fun to pick a project that gives you a pretty output, and it's fun to try on something new using that technique. There's a ton of things I could do if I had more time. Now I have GCC 11 working. I had to actually rev some libraries to get it, like some open source libraries. I had to do pull requests on Friday night to try and get them shuffled up to get them to build with GCC 11. But I would have liked to have tried standard Rage to see whether or not that has all the things I need from it in order to replace Range v3. It would have been fun to spend more time on the DoD. Thank you so much for your time and this opportunity to talk about it. I think you should go and write something super cool. Thank you. And I've got some questions, I think, in here, and I've got some bonus slides as well, because there's more. There's always more. Any book resource recommendations regarding data-oriented programming? I am definitely not an expert. I'm hoping somebody else can chime in about what a good way to learn data-oriented programming. My sort of beginning and ending is just like the instinctive stuff that I did in the late 1600s, or it seems that way, when I was in the games industry and was writing everything in C, which sort of naturally that way. But then Mike Acton's, I think CPPCon video 2016-ish era, it was pretty good for getting a good grounding on it. Someone's asked, is this the case for compiler annotations? It's funny. So many people have said, hey, have you tried likely and unlikely? I have tried likely and unlikely, those specifically. And of course, the trick here is it's not likely or unlikely, it's unpredictable. And that's another annotation that we could potentially do. And then to wrap the whole thing in, but this is predictable, I don't know. It's a very difficult thing, and it's a sensitive thing to rely upon. So I don't know what the right solution is there, but it did occur to me too. So thank you, Philippe. Pessimized scenes where there are huge triangles. That's also true, Michael. Yeah, we do extra work, but the work is relatively cheap. And in fact, yeah, I was moving things up and down a little bit to whether I should calculate V first or just early out on the U, and that definitely helped it. And the code base, yes, the code base is available. Pretty much everything I ever do is on GitHub. So it's pt dash. Oh, I can put it in the chat in a minute. But pt-3-ways on my github.com/MattGoldbolt. Someone I hopefully can tap away and find it and then post the actual URL, so you don't have to watch me peck at the keyboard. Thank you, Mike. Yes, that's awesome. Thank you, everyone, for your time. And I will continue to answer questions if people want to interrupt, or I can kind of move on to the thing. All right, I'm just going to do quick bonus slides while people are sort of making their excuses. This was my attempt to write a, hey, compiler, please don't try and combine these two bool checks into please definitely combine these two bool checks into one thing that I can jump upon. This sort of replaces the logical, sorry, I keep saying logical, the bitwise OR between two conditions. And it involves an hilarious and not to be emulated or taken seriously use of the volatile keyword here. This does work. This made it go 76 seconds, which was great. But unfortunately, most compilers see the volatile keyword. So you can see what it's doing here. It's like assigning x1 to this volatile, which is now required to read back out from. And then I'm ORing in x2 into it, which again forces it to have to do it. And then returning through it. So again, finally, begrudgingly, the thing that's actually going to be jumped upon is this result, which has been successfully laundered through this horrific volatile. So that now the compiler won't jump individually on x1 or x2. It has to look at the combinations therein. And it's pretty disgraceful and not to be recommended. It brought the time down to 76 seconds, which is good. The problem with it, though, is that now you'll see the code. And you see, this is where I could have used a compiler explorer, I think. But you see the code, and it's now unnecessarily reading and writing and doing manipulations to the stack. And most sensible compilers take one look at the volatile keyboard and go, keywords, sorry, and dust their hands off and say, okay, you're on your own now. I'm not optimizing that. So, you know, putting volatile is not a good thing. And so, again, don't do this. I'll catch up with the comments in a second. I'll just go through this. So then I wrote this, which is even less defensible, maybe more defensible. I don't know. It's not very portable. So I'm using inline assembly to say, no, for the love of the children, definitely OR these two things together and use that. And the compiler can't see through this ASM. At least GCC can't. Clang is a bit smarter. And so this is just ORing the two values together in assembly and then saying, hey, return that value. And the compiler makes no guesses as to what the heck happened with that. So it has to jump on that particular thing. And that one brings it down to 71 seconds. So it's even better than the volatile trick. And then finally, I compiled it with GCC 11 after I fixed all the build issues. And the same code just goes down to 62 seconds, which just goes to show, you know, upgrade your compiler, turn on all the flags you can find. And if I replace this NE2 with just return x1 or x2, it goes back up to 120 seconds. So it's really sensitive for this one. It's a lot of fun. Yes, volatile is not trusty for anything. Basically, if you're using the volatile keyword, you're almost certainly using it wrong, unless your name is Jeff Bastien or you spent a lifetime writing embedded systems. I'm prepared to be wrong on that front. So thank you, everybody. I know I talk at 100 miles an hour, and this was no exception. And I know I got a bit lost in the middle, but it's been a lot of fun. I'm now just scanning to see if there are any unanswered questions. But I mean, depending on how you hosts feel, you can do hand raising or people can just jump in.
Yeah, thanks, Matt. I think we'll just give them another second to see if there's any additional hands, if someone wants to speak up on the voice. Personally, Matt, I watched this talk, I think it was the original talk at CPPCon.
Right, yeah.
And I do remember you ending it, a few slides back. And it's
Right.
like kind of reading a good book and getting to the end and not getting the ending you want.
That's right. That's exactly how I felt too, right? I did have some ideas. So the very, very first time I gave it, I had literally no ideas. But by CPBCon, I had some idea. So it was definitely the branch predictor did it in the murder of mystery that came out of my otherwise sort of po-faced C++ talk. So
okay,
yeah,
good.
so
Well,
good. If people want to look at the C++ talk, yeah, you can. It's on the CPBCon website, and the slides will look. It will be if you do go back and watch that now. Obviously, I don't have a script, so it'll be very different every time I present it. But you will have deja vu if you watch the other one, or déjà vu, which is like the anticipation of seeing something that you have already seen. I think there's some French folks, I'm sure, French-speaking folks on the call who can correct me.
all right. Looks like we have a question from Tony. So, go
ahead.
I just want to I want to see what happens when you get the random number generator out of there where it doesn't belong. That's the one. I'm about to download the code. I think I'm that close.
It should hopefully build again. It used Conan's for its dependencies, and I don't know if you know, Conan went through a sort of period recently of kind of going, hey, we're changing the way we do things, which broke all the old builds, and I'm still grumpy at them for doing that. Especially as I was trying to git bisect like where a performance degradation came in very recently. I'm like, and I can't even build the old version. Grr. But yeah, it should work. And if it doesn't, ping me, and I'll help you make sure it does work. It's the thing I love is making sure that code.
I would also like to know, from someone who does functional, like there must be a model for random numbers in functional world, right? Like because they've managed to model everything as functional. So I don't know how to.
I'm sure the word monad is about to enter this conversation.
Most likely,
the random number monad that you just invoke and get back a new thing or something. I don't know. Somebody save us from trying to sound intelligent about something we have no idea.
Yeah. Just say monad. I think that's the right answer always.
Yeah. Which is, I think, an Indo functor in the category of monoids or something. Damn, I wish I'd committed that to memory. So Michael Dawes just put in the chat that this was in the same branch prediction issue. That's interesting. Yeah, Andrei Alexandrescu and I have chatted about some of these things before. It's quite fun. Yes. And yeah, the standard random number generator is not fast at the best of deals. And obviously, a lot of what we're doing is random number generation to parameterize all these things. I did try a cheesier random number generator than the Mersenne twister, and with predictable results of like, oh, that's nice. I've got the same pattern all over my screen that like untuned television look to it because it would use the same repeating thing over and over again. So, but it was faster to use a faster random number generator, but it didn't look as nice. And it just makes me take my hat off to, there are a number of good books about how to do this kind of stuff. There's I've got this one just happened to be on hand, Peter Shirley and I can't remember his name, but Keith Morley's realistic ray tracing, which is very specifically ray tracing. And then there's another one that's like a whole engine, a whole 3D, like Pixar level quality, open source engine that is just chapter by chapter. They just go through the whole code base and say, this is how we do this, this is how we do this. And I've got about a third of the way into that, and it's just amazing. And they managed to get like Pixar to give them some scenes from like The Incredibles that they can render, which is mind-blowingly awesome. So you can go a long way with this stuff. But given how ridiculously slow my toy implementation is, it just gives you an idea of the orders of magnitude of improvement you can get if you're not stupid on purpose. Exactly, Kate. Yes, that's the XKCD reference you. Did I try? I'm trying to catch up now with the chat here.
I think we're good. I've been watching. I think.
Okay. All right. Yeah, we said yeah.
There was one question do you recall trying a no inline function that combines the bool?
That's an interesting one. I did not, and if I were a better person, I'd have it up in Compiler Explorer. We could just go and hack the code right now and give it a go. But actually, what I found is I'm using link time optimization, and it the thing that I'd managed to trick myself with before is that with link time optimization, you got this very spooky non-local action. You could make a change to a bit of code a long way away, and then suddenly the compiler didn't see an optimization that it used to see inside your hot loop here. So that was a surprise to me. So sometimes this thing here would actually be a combined CMOV and a jump already. Sometimes it would be the two jumps that we saw when it was bad. And then sometimes if I put the single OR in, a non-local change somewhere else would make it change its mind about which one it was going to do. And that was extremely difficult. And that's why, having a notebook of what the hell the changes you've made are before you go like, why is that now slower? What did I do? What have I changed? Came to mind. I don't know quite what I still don't know what it was. I would have liked to get bisected to be able to find it, but unfortunately, something code M, something problem, but yes.
Okay.
Yeah, it's amazing. So thank you, everyone. I think, is that everyone covered?
I think we're good. Yeah. So let's give another round of applause for both Tasso and Matt here.